video review of the semiconductors, and today's topic will be about the first subthreshold swing, and second complement MOSFET, and lastly third SCE, short channel effect. So first will be about the subthreshold swing. We know that the drain from the source current equation is same like this. So that if there is the gate on voltage, if the voltage of the gate jump the threshold voltage, then the channel will be induced. So let's guess just gate and source drain, they have little with n-type silicons, and here when the voltage is over the threshold voltage, there will be channel induced here of the electrons induced. So and one more thing, if there is the voltage induced in the drain part, then current will flow by the difference of the potential between the source and drain. So this equation is looks like this. Of course, for EDR there will be some slope that has slope linked with VDS if the VDS is not too even. But in real life, within the manufacturer therapy or anyway, there will be some difference, and before the threshold voltage, that gate voltage is induced. So I mean, at here, though the gate is not over the threshold voltage, there will be for more easily small channels, not the channels. We know in the MOSFET part, though there is no accumulation of strong inversion, we learn about the weak inversions. Of course, here's the density of electron is not stronger or same as the bulk side. In weak inversion. But we know, since there is some electrons that cannot, there will be some electron flows if there is voltage induced in the drain or source. So just use things like this. Some little channels by the weak inversion, so current will flow somewhat little. So there is problem. We know that before the strong inversion, it is turn off state in MOSFET. So it has problem. Before turning on the switch or the PET, there is current flow. So it means there is assumption of power, and it will make the more extra consumption of the power by the electron flow or current flow. That's unexpected. So ideal graph will be like this. After the threshold voltage, and for real world or practical will be more some expressional graph like this. So, but since the current amount is very small to exactly see, so we call this, we see this as a localized values, so we call this as a threshold swing. Maybe, so we can call this by the 10 times the current blow up, we call 1 millivolt to up. Okay, so see, there is some source and drain and gate for gate energy band diagrams. There is more the difference between the gate and source will be the potential relativity gate and the voltage, the inducing source here again. And here will be about the potential relativity gate. And here will be the potential relativity gate and the swapping the voltage of drain. So we know, since here the energy gate difference is more smaller than drain between the gate, and there will be more electrons of being probability. Of course, here we go smaller. And we know if the drain source is applied already, then current will flow. Of course, in ideal situations, we can see by these energy barriers, electron or hole, anyway, the carriers can pass. But in real life, the carriers get more higher energy than this wall. So very small or little carriers pass through this and move. And it makes the current flow. So this is the problem of and why we see about the subthreshold swing. Okay, so maybe the concentration will be linked like this. Is potential of Boltzmann constant and temperature and the gap between AC. So apply the localizations, we can apply this equation, the length width between the drain source and in the subthreshold that between the voltage of the gate is smaller than the threshold voltage. Okay, so by more localization and subsetting and dividing, we can get the subthreshold swing equations. 1 millivolt per decade. It means by the 10 times the millivolt increase, by the 10 times millivolt, the current increase, by the 10 times current increase, how many millivolt it will spend for this? So it means if the subthreshold swing is more smaller, there will be more saving of the power consumptions. So, okay, we can say it like this, and N means the coupling coefficient between the capacitors of depletion and oxide, and the internal trapped capacitance. So, what is the internal trapped capacitance? So, when junctions between the oxide and silicons, the surface is not firm. There will be some fractals or somewhat empty rooms, so electron is trapped here. And it will make the capacitance by the electric potential difference. Okay, so if the coefficient of the coupling is more smaller and smaller, and when it equalizes to 1, there will be more smaller subthreshold swing, and the graph will be moved like this. 10^95. Yes, here is the voltage fluctuation, all the voltage, it will be like this. So, if the coupling coefficient is 1, then by the Boltzmann's limit, Boltzmann's limit, the subthreshold swing can't never be over than subthreshold can't be under the 60 millivolt. Okay, subthreshold is the second about the Cmos, complementary MOSFET, integration of P-type and N-type FET. So, if I draw the Cmos FET, P-well on the left side. Okay, so it will be like this. So the total body is about the P type of freight. So if there is P substrate, then there will be problem between the heavy doped P-type silicon that linked with source and drain and between the substrate or body. So we make an N doping or N wall to block from the P substrate to the source and drain that dope with heavily to the P-type. So more logically and simply draw, we will like this. So source and drain and source sequentially. Let's call this apply as the VDD. And the gate induced voltage will be the voltage of input, and the output between the drain and drain will be about the V output. Okay, so let's get there is a load or capacitor in the middle between the voltage of output. So let's get I induce the voltage in the input voltage. So at first, the current will flow from the upper top VDD and will flow from following the P MOSFET, and after passing the middle between the drain and drain, you will go flow to the N-type MOSFET. So first, if the V input is lower than okay, for first condition, the P-type MOSFET threshold voltage is bigger than the V input. Then here will be the P channel induced and current will flow. But here the channel is not induced yet. So current will flow just from the VDD and V output. Okay, so current will flow like this. Okay, so the first condition and second, if the voltage is big enough, so green is more bigger than the threshold voltage of the N-type MOSFET threshold voltage. Then current will flow. Current must flow here from here. Since a P-type MOSFET threshold voltage is smaller than the threshold voltage, the gate voltage induced. So P-type channel will be not induced. Since here is the plus, so Hose will not be attracted and gathered. So no channel in the P-type MOSFET, but in N channel there will be channels induced here by the polarity of attractions. So current will flow from the load of the capacitor and will finally go to the ground. Okay, so by this notation, we can get something logically about the inverters. So if I get high input, then the output will be about the low. And if I put the low input, then output will be about the high. Okay, so we can use the CMOS as a logic gate. So we know about ID and VD relations equations by this graph. Okay, so this graph will be about the N-type output between the VD and ID. So all the P-type, just we know the P-type will be here, but for the comparison of this graph, we do like this. Okay, so there is some application relation between the P and type MOSFETs, relationship between the VD and ID. So here it is. So here is the problems. Between the N-type MOSFET and P-type MOSFET saturation, there will be the channel induced, So here is the problem. If there is one gate open, there is one gate must be closed. But by this graph and this graph, we know we can state like this. Oh, there is some problem. The two paths are all closed in the same time. So at this moment, there is some problem. So Ideal graph will be output will be like this, but for real, somewhat gradually, exponentially graph like this. Sorry. Okay, so CMOS can be used as a logic gate within some delays. If there is some resistors and capacitance, we know about this. So delay will be linked like this. So okay, so roughly about fan out. Fan out means how much logic gate like PMOS, AND gate, NOT gate, NOR gate, XOR gate, NOR gate, anything else logic gate can be linked to the one logic gate in CMOS. So we know. If there is capacitor here, then the output will be about like this. The capacitance or the voltage of the capacitor. So let's get we link the loads here by the carry up or on flow. The capacitance of total is this. Okay. If it is in serial, so more load and load induced, the resistance will be down and the current will be more up. So there will be some overflow or overload. So there is something important about the panel. How many we can connect? This will be settled for the safety or to block the power consumed heavily. We will set how much we can link from the CMOS to another logic gate. Okay, here is the end of series. Here we talked about the channel length. If the channel length is long enough, so like this, long. And for now, in this lab, for this century, the semiconductor is getting more smaller and smaller and smaller. Okay, so let's guess. About 20 years ago, there was big televisions. Its size is like us, but now, within a bound size, there are cell phones that can see the internet, TVs, and even can use SNS that only can use in the computers. So, by the smaller size of the semiconductors, we developed more effective size and more costumes downside. Okay, so short-term effect by the smaller and smaller downside of the semiconductors. Okay, for the MOSFET, the channel length modulation always been a problem. So let's get. There is about 10,000 military soldiers, and one shot of the mortar, and 30 people died. But there is no big difference between the total of the army soldiers number and the after the mortar bouncing. But if there is 100 and mortar attack is again happened, 30 people died, and there is only 70 people remained. There is big difference. So by this, we can see how the difference between the long channel modulation and short channel modulation is very different. Okay, so what is short channel effect? As I said, yes, there is some short length of the path here, and I induce the voltage. Okay, there is heavy doubly doped silicon that function as n-type, drain and source. So we know this is the substrate. Okay, so depletion will be started, but we know the heavier dot, there is the heavier dot here, and lightly dot relatively to the p-type silicons. The depletion will be larger to the light dot. Okay, like this. actually too. So this program will make the depletions more larger and enlarging. Okay, so let's guess. We just induce the drain, the voltage, then we know this is the n-type silicon, so I just induced the plus voltage to the drain, then the depletion, then the silicon is the silicon of the p-type, n-type. Okay, so I just induce the voltage of positive in the n-type, the drain, then by the reverse bias, the depletion region will be more larger. So larger, and finally the depletion between the source and P substrate and the depletion that lies between the drain and the body has met, like some tunnel or load meeting. So there is problem. There is electrons can pass through here. So what it means? Even though I don't make a channel, the current can flow from source to drain. So it will make the current that I never wanted or induced. So this is very big problem. Relatively to the have a similar relation to the power consumption, overflow, anything else. So just like this, I just turn off the switch off. Okay, and I slept. But current keep flow, then it will make some fire problem or the power consumption problem. Okay, so one more thing. As the depletion meets the current will flow, we call this situation as a punch through. And okay, so we can see the more voltage induced in the drain, there will be more current flow from the source to drain by the electrons passing by the depletion region's tunnel. So, okay. Yes, there is some ID and VD relationships by the localization scale. Okay, shadow. For either case, substrate will be 60 millivolts and the coupling coefficient between the capacitance of the oxide and depletion and the internal trap capacitance is relatively coefficient is 1. But by the VDS increase, the capacitance between them will be coupled and more larger. So it will be more surely bigger than this one as more VDS increase. Okay, so if it's like this, the slope will be more flatted. Of course, in localization there is the slope is reversed. So more slope the flat, the more energy consumption is more happening, power consuming. So the more flat the graph has the slope, there will be more power consumption. So more steepness of the slope will be more good for the semiconductors, for the Cmos. Okay, so there is three solutions to prevent this consumption unused. First, heavily dope the piece of body more. Okay, by the doping, the depletion region will be same or reduced relatively to the P heavy plus and lightly doped. But okay, per second, make like a shield that is very high resistor like oxide. But this problem is that it can't heat sink. I mean, it can't emit a heat. So overheat problem will be happened. And third, also heavy doped silicons inside like this partially. But here's some problem. Channel length modulation will be limited, so people changing the doping relationship will be what the length will be this. After changing will be only this. So current flow will be reduced relatively. Okay, the three solutions that I just taught is not useful currently. There will be another solution. Okay, thanks for listening to this end of the review video. Thank you. Bye.